So, hi. Today we are going to talk about some sorting algorithms, and we will talk about three very basic, very like base sorting algorithms. It's insertion, selection, and merge sort. So, what's the point? Why are we doing this? To create your professional, your engineering thinking. So those algorithms are basic, and insertion and selection sorts are very slow and not really useful in real life. But for you, it's very important to uh, train your brain to be able to create your own algorithms. So we training on those sorting algorithms. So let's start. Wow. Okay, so let's do some revision. Bubble sort. Okay, this is not GIFs, and this is a problem. Uh, okay, we will do it on the whiteboard. So, do you remember a bubble sort? Bubble sort, I think we don't need to draw it. Just the bubble sort, we check in two elements, we find the bigger element, and we move bigger element in the right? What's the big O of bubble sort? Yeah, so big O of bubble sort is n squared, and what's the best possible O, big O for bubble sort? N. Yeah, if all elements already sorted, we will traverse our array only once. So this is complexity, it's linear complexity, it's n. So let's start from the selection sort. In selection sort, every so our algorithm work in this way. We trying to find the minimum element in our array. So we have some sort of variable min, and we traversing our array and trying to find minimum element. So 5, right now it's 5, then 2, then our min became 2, 7 no, 0, then it will be 0, 1 bigger than 0, so no, 5 bigger than 0, so we don't change it. And after this, after we traversing this array, we swapping elements only once. We swapping our current element and our min element. So in this situation, we swapping element with index 0 and element with index 3, our minimum element. And after this, we will have such array, and we consider that this part is already sorted. So now we starting our new traversing of element and our new search of minimum element. So now it will be 2, then 7 bigger than 2, no, 5 bigger than 2, no, 1 less than 2. So our min element is 1, 5 bigger than 1. So now what we need to do? Swap what with what? Yeah, so we need to swap our current element, and our current element is like next one after our previous current, and we need to swap it with our minimum element. So we swap in those elements, and so on and so forth, and then we will have our sorted array. So who can tell me what's the worst scenario for this algorithm? What's time complexity?
Every element's like they're the same.
And
Mhm.
Just minimum by each of them.
Yeah.
Not just like based on
No, it's O n squared. Because we have it's like in bubble sort. We need to traverse all elements and time, because we need to traverse all elements for every element in array. Makes sense or not? Okay, but what's the you can remember you said that for bubble sort, best scenario is ON. But what best scenario for this algorithm, for selection sort? What? No.
less bigger.
Hmm?
Less or bigger.
Totally not less.
and
Maybe
square.
it's square.
Yeah.
Because we still need to traverse, we still need to check all of them. It just won't swap.
Yeah. Yeah, because in bubble sort, we check elements every time. So we can do some, we can traverse our array only once and be sure that this array is sorted. This is a part of bubble sort. But here we need, we have like a little bit dumber algorithm that find min element and swapping it. So even if we have unsorted array, we still traversing all elements to be sure that there are no min elements like in the end of array. Does it make sense? Okay. So this is selection sort. Pretty. I think you will not find practical use for this, but it's interesting to train your brain. I see it this way. It's for training your professional perspective. So, insertion sort. I have something strange with insertion sort, because I don't understand how it's work. Okay. So, insertion sort. Let's start from beginning. We have our unsorted array. What we do in insertion sort? We have our current element. For example, let's start from the element with index 1, and you will understand why. So we have our current element. It's right now 2, right? And we check if it's less than previous element. If it's less than previous element, we swap it already. Okay, in this situation, 2 is less than 5. So we swapping them, and we have such a line. Then our current element is -7. And here we check -7 less than previous element. So we swapping them, and then we check if our, so now our current element is with index 1 and it's -7. So we swap once more. So the main idea of insertion sort is that we going through elements one by one, and we move our element one by one in this direction. So it looks like this. Sorry, guys. It's very embarrassing, but yeah. So we swap those elements like this, and at the end of this iteration, we will have such structure. And then our current element will be with index 3. This is 0. And we check if 0 less than 5, we swap them. So now it will look like this. Then if 0 less than 2, we swap them. We swap them. Are 0 less than -7? No, we stop here. And we know already that if this element bigger than previous one, this means that it's bigger than all elements that later that this element. Yeah, and we do this for every element. Like the same logic with 1. We start. We check 1 less than 5, then we swap them. 1 less than 2, we swap them. 1 bigger than 0, so we stop here. This is an insertion sort. What time complexity for insertion sort?
N square.
N squared, right? And what is the best n, right? Why?
Because we need to check every element of the array, yeah. Just once, so we don't need to go n square times, just like one loop.
Yeah, so we don't need to swap any elements if they are already sorted. We just check every element. We check previous one, and we can see that those in the right arrangement, and we just move one by one once, and it's O(n).
Yeah, it's really similar to bubble sort. It's just like traversed.
Yeah. So those algorithms are very basic and very it's easy to understand them and easy to write them. When you will write those algorithms, you will be surprised how easy they are. They are like bubble sort. But with this we have a problem. They are too slow. O(n) square is not okay. It's very, very slow. So we need at least O(n) log n, at least. So here, here we can match merge sort. So what the idea of merge sort? Let's create other array. So as you can see on the slide, merge sort is following the divide and conquer approach. Merge sort is a recursive algorithm, and it contains two main operations: is dividing, and merging. So let's talk about those operations. First is dividing. What does it mean? It means that if we have some array, we will recursively divide it and create a copies of its array. So, but like in binary search, this is a halves of our array, and it will be recursive. So we will create an array with only two elements, and we will create other array with only two elements, and we will create also array with one element, and we will create array also with one element, and the same thing for this sub array. So this is concept is called concept of division of our array, and you will understand why we need to divide it. But I want to prepare you before we'll use it in real algorithm, and then merge. So we divided those elements, and now we need to merge them. And merging is very simple concept where, for example, we know that we have two sorted arrays. For example, 1, 2, 7, 9, and we need to merge those arrays. So if we know that those arrays are sorted already, we can easily create an sorted array with those elements. So, for example, how we will do this? We will check our first element here and first element here. And we will try to find one that less, smaller one. So in this situation, it's 0. So we write in our merged array 0. And we move this pointer to the next element because this element is already merged. Then we compare this element and our first element in first array. This element less than that. So we write that one and we move our pointer to this element. And now we're comparing those two elements. 2 less. So we write 2 in our merged array. And we have only one element, we write this element here. So this is like a shuffling cards, like in the casino. When we have two sorted arrays, it's very easy for us. This is a O(n) operation to create sorted array from two other sorted arrays, right? Okay, so let's move on to our merge sort. So what we're doing here, our algorithm will divide our recursively. Keep it in mind. It's very hard to understand what you will, but keep in mind that everything that I'm telling you is in a recursion. So basically, we have one operation of dividing our array. We have left and right, like in binary search. In this situation, left, let's give them indexes. Left 0, right is length -1 is 7, and we finding our middle element, and based on this middle element, we dividing our array to 2. So now we will have 2 arrays. And this operation is recursive. So for this array, we also will have left and right. Also, we will divide this array to 2. And recursion, we will have 2 arrays with 1 element. And in merge sort, we want to divide our array to the like smallest possible array. So array with 1 element. The same here. And also here. So now we have totally divided arrays. And now we can start our merge process. So, for example, we have LP, our left pointer, and RP, our right pointer. And this pointer is our index in our array. So we start from 0. And this is 0 elements. And we compare element with index LP and element with index RP. We compare them. 2 less than 5. So we merge them in our previous array. And we can imagine that this array is empty, and we first of all, we like saying that our 0 element is 2, and then we have only 1 element in our array, so we automatically pass it to the left spot. The same situation here. We have only 1 element in every sub array with 1 element, so LP RIP is zeros, and we check if 0 less than 7, it's less than 7, so we move 0 to the first element and 7 to the second element. Okay, then we do the same operation with those sub arrays. How does it work? We start with also LP equals 0 and RP equals 0. We compare 2 and 0. 0 less than 2, so we send our first element in our merged array is 0. Then we move RP to the next element because this element is already merged. So now our RP equals 1. So now we compare what elements? 2 and 7, because our LP 0 and our RP 1. We compare 2 and 7. 2 less than 7, so we merge 2 to the second element in our merged array. And what we do? We increase LP. What? Yeah, absolutely right. Because this element already merged, so we can move on to the next one. So now LP, we comparing elements with index LP and RP. It's 5 and 7. 5 less than 7, so we write 5 here, and we left with only one element, so we automatically write it here. The same situation here. Do the same operations. So who can help me with this? Maybe Antonio. So we have LP0 here, and here what we do with those elements. Right pointer, left pointer. For one less than 9, so we will switch them by pointers. We not switch them. We include in one. Yeah, because this is other array. Those two arrays and this array are different one. So we don't switch them. We write those numbers in this other array. Yeah, the same situation here. We check them, we write them. Then we need to do the same operation with those two arrays. So, Emilia, can you help me? How can we merge those two arrays in one merged array with 4 elements? What's the algorithm? So we have LP left pointer equals 0 and RP equals 0. So we start with those two elements. What? Okay. Yeah, can you describe the algorithm of merging those two arrays in one sorted array? Okay, Anton.
So like LP and RP, so
Yeah.
1 and 3.
Yeah.
And write them down in ascending order down like bigger array.
Yeah, so what I need to write?
Write 1.
We write 1, but we don't write 3 at that moment. Because imagine that here is not 9, but 2. And if we will write 3 right now, then this array not going to be a sorted one, right? So we wrote 1.
So we increase our LP by
Ye-
1.
Mm-hmm.
Then we compare again.
Yeah.
So LP is bigger than RP.
Mhm.
So we write 3, and then we increase RP by 1.
Mm-hmm.
Or compare it again, and 4 is bigger than 9, so we write 4 and then 9 because like we reached the limits.
Mm-hmm. Yeah, right. So now we have two sorted arrays with 4 elements, and what we need to do is to merge them in our main one. So Tanya, can you help me?
Oh, okay. Now,
So we start with zeros, right? 1, 2, 3, 4, 3. Mm-hmm. Mm-hmm. Yeah. Mm-hmm. No, then we need to. Mm-hmm. Then what we compare next? Why? Because we're comparing elements with indexes LP and RP. And our LP is 1, so this is 2, and RP 0, so this is element 1.
Yeah.
Mm-hmm. Mm-hmm. I'm a computer, and you're a programmer. What I need to do next?
LP1 and RP1.
The big error,
Okay, we change LP
right?
to 1.
Mm-hmm. Okay.
Then there are 2 and 3.
Mm-hmm.
And 5, 2.
Yes.
Okay, then we change LP to
LP, right?
then
Mm-hmm. Yeah, so I think I need to repeat after you for online guys. So then we compare 5 and 3, writing 3,
then we change LP to
change RP to 2 because we wrote right element. Mhm.
5 and 4.
Compare 5 and 4.
We can write 4.
Mhm.
Change LP to
LP.
okay.
Why?
We can write 5.
No, 4 less than 5.
Should increase LP.
Yeah, we should increase RP because we increase that pointer where, like from which side we used our element. Because if we write 4, we don't need this 4 anymore, so we can use only elements that next to 4. So we increase our RP. Okay. What could we compare next? 5 and 9. Mm-hmm. Okay, and what pointer we are increasing? Mm-hmm. Okay. 7 and 9.
Right.
Yeah, like we increasing, look, automatically in the algorithm we will increase LP, and we have only one element, so we write it here. And we have our sorted array. Cool, right? Very interesting. And can you imagine how to program this?
Oh,
No. Yeah, it will. please, I beg you, please don't use ChatGPT. Try for like 15 for 30 minutes, sit and try to create this algorithm by yourself, because it's so interesting to recreate this abstract stuff to working code. It's so fun. It's like better than stand-up comedy. Okay, what time complexity of this algorithm? Hmm?
Just big for us, at least.
No, it's smaller than, it's better. Not smaller, it's better than bubble
It's
sort.
n logarithm n.
Yeah. It's O n log n. We want to know why. So in this, in such form, we can, I can show you it's purely mathematically. So we have like our depths of recursion, and we have a number of elements in our array and number of operations of checking and merge when we merge in elements. So when we merge in elements, I already said you what's the time complexity of merging elements. O(n), because it's linear process. We check two elements, we compare them, we write one of them, and we do it so on and so forth. Like if it would be if you will imagine a cycle, a loop, this is going to be only one loop without inner loop, right? So here we have n elements and O(n). And here, what's the number of, what's the depth of recursion? It's log n, like in binary search. Because here, for example, we have 8 elements, right? N equals 8, and log this base 2 from 8 is 3. And here we have 1, 2, 3 layers. Makes sense? No? Okay, so binary search works with this concept that we binary splitting our array, and the time complexity of binary operation is log n, because because it's math. I don't know. Log base 2 from our n is a number of is a worst scenario of binary operation. So I don't know. Is this do you understand this concept? Hmm? What?
I said a bit understanding.
Okay.
Yeah.
Okay. So in this situation, for example, in bubble sort, time complexity is O(n) squared, because we have two loops inside of each other, and we traverse all n elements in those loops. So we have traversing of all elements for every element. So it's n multiplied by n. And here we have traversing like some linear operations of merging elements n times, and we multiplying it by the depth of our recursion, our number of this dividing process, and divide our array. We divide our array log n times. So time complexity of this algorithm is n log n. And I prepared a practical solution why it's important to have algorithm with such time complexity, and why O n square is bad time complexity. So here you can see effect that has a name, a pixel sorting. So what's the point? Every image on your screen is a set of pixels. This is, we can say, this is a two-dimensional array of pixels. And you can imagine every pixel as an object. Object with only, for example, only 3 fields, red, green, and blue. We can have any color. This combination in some combination of 3 colors, red, green, and blue. So we can imagine we have a class pixel. There are 3 fields, RGB, and we can calculate using those numbers. We can calculate brightness. We can calculate I don't know even what else for only 1 pixel. For example, brightness, right? And brightness will be a numerical value, because RGB, red, green, and blue, this is a numerical values. This values between 0 and 256, right? Because this is a 4-bit colors. So every color in pixel is a 4-bit. So 4-bit is the maximum value of 4-bit value is 256. Okay, so we can calculate our brightness, and our brightness will be a value from 0 to 1. And we can sort our pixels like our numbers in array using those values. So we can say that this object of pixel and this object of pixel, this have brightness 105, this have brightness 101. And we can say we want to swap those pixels, and we can swap pixels in an image. And this is what happening here. We can see that there are some patterns, like here, brighter 1 pixels at the bottom and darker one in the top. So we have normal image, but then we sort pixels, we move those pixels on the image, and we have very interesting effect. So I created this image because I found this image and I thought, wow, it's so cool. I want to recreate it, and I wrote an algorithm for pixel sorting. And I was lazy when I was creating. I was excited, and I didn't want to create some like complicated sorting algorithm. So I used bubble sort. And for such image, like 4K image, we can calculate number of pixels. And if we have time complexity n squared, we have such amount of iteration to sort all of those pixels. And this bubble sort, I remember it's like 1 minute for every picture. And it's so slow. And then I tried merge sort. And it became like 5 seconds. So this is so big of a difference. And why is this? If we will look at our diagram, we can see that the bigger and the worse it became those algorithms with such time complexity. And other situation with n log n, the bigger n, it's not so bad when we use bubble sort, for example. So this is a practical explanation why it's important to not to use certain algorithm with n square time complexity. And if you want, you can recreate this, because you can do this in any language. You just need to find a package, a library for image processing, and after this, it will be very easy to just upload any image and write your own sorting algorithm to sort pixels, because pixels is just an object, and you can manipulate them with this image processing library. So, do you have any questions?